Hi, this is Andrew with Mock 2 Drop, and in this video I want to talk about hypothesis testing. I know that this concept in the quant section for level 1 can be a little tricky to understand, so my goal of this video is to go over an example that I think will be a good foundation in helping you better understand hypothesis testing. I'm going to break down an example and try to explain it in a more simplified approach. So we're going to work with this one example throughout this video. I'm going to break it down and try to make it more intuitive. So as we go through this video, I'm going to keep the portion of this example up on the slide that's relevant to what I'm explaining, just so you have a reference to go off of. Alright, so let's take a look at this example. We gather 30 stocks and determine that their average return, or mean return, is 11%, with a standard deviation of 25%. We can assume this is on an annual basis. The population, the stock return, is expected to have a mean of 9%. In other words, this is what we are going to hypothesize. This is also known as the null hypothesis, which is what we're testing for. Now, when we talk about the population of stock returns, let's use the example of average stock returns for U.S. traded stocks on exchanges. Now, we don't know if the average return of all U.S. stocks traded on exchanges is 9%. That's why we're going to test this hypothesis using a sample of 30 stock returns. Now, you might be asking yourself, if we know that the mean return of the 30 stocks is 11%, isn't that different from 9%? Well, yes, it's most likely going to be different. Let's say the first stock you pick for your sample happens to be Tesla stock. Well, the return is probably going to be much different from the mean return of all U.S. stocks traded on exchanges. But as we sample more and more stock returns, you should start getting closer to that population mean. So in this case, we chose 30 stock returns as our sample. So there's most likely going to be a degree of variation from the population mean. And this brings us to our next part of the example, which is we would like to be 95% certain that the corresponding confidence interval around the sample mean contains the population mean return. We're going to talk about this more on the next slide. Then in the example, it says that this corresponds to a critical value of 2.045. Now, this value is most likely going to be given to you on a test question, usually in the form of a chart where you have other values and you have to pick from it. We're also going to talk about that in more detail as well. And lastly, this question asks, based on all this information, what is a calculated t-test, and do you accept or reject the null hypothesis? In other words, do we accept or reject the null hypothesis that the population mean of the stock returns is 9%? Okay, so we covered a lot in this slide. Now we're going to break this example down even further. So I mentioned that I would bring over the portion of the example on the slide that's relevant to what I'm explaining, just so you have that as a reference to go off of. You can see that here on the top right. So here's a visual of what we're trying to accomplish here. We have a sample of stocks, and the mean return for those stocks is 11%. And the question asks, are we 95% certain that the confidence interval around the sample mean contains the expected population of 9%? In other words, what we hypothesize. Keep in mind that this 95% is a probability. So based on sampling 30 stocks out of all traded U.S. stocks, is it possible that if we create a confidence interval around that mean return of 11%, that the population mean will fall inside that range? And that's what we're going to test for here. But we don't need to determine the lower and upper range of the confidence interval in order to answer this question. We're actually going to calculate it a different way using what is called a t-test, which we'll cover on the next slide. Now, at the end of this video, I'll show you what this confidence interval looks like and how we can determine the lower and upper values. So here's what our calculation for a t-test looks like. First, we subtract the population mean from the sample mean. Then we divide that by the sample standard deviation divided by the square root of the number of samples. Therefore, we have 11% minus 9%, and then we divide that by 25% divided by the square root of 30, and we get 0.44. So you're probably wondering, what does this t-test value of 0.44 mean? Well, if you remember, I said that we would go over the critical value of 2.045 in more detail. So this t-test value of 0.44 is going to be compared to that critical value of 2.045 to determine whether or not we reject or accept the null hypothesis. But before we come to that conclusion, let me go over how we can determine the critical value. So in my example, the critical value of 2.045 was given. This most likely won't be the case on an exam, as you'll probably be given a chart like the one you see here. So as you look at this chart, you can see that our critical value of 2.045 corresponds with a DF, or degrees of freedom, of 29 and a p-value of 0.025. And you might be asking yourself, why are we using 29 as degrees of freedom to determine the critical value and not 30? What this is saying is that we can freely guess 29 of the stock returns if we know that the mean return of the 30 stocks is 11%. So once you have the returns of 29 of those stocks using simple math, you can determine the return of the 30 of stock given the mean return of 11%. So that's why the degrees of freedom is determined by the number of stocks in our sample minus 1. Now we also have what is called a p-value. This is simply 1 minus the 95% from our example, which is 0.05 or 5%. You can think of this 5% as kind of the opposite of the 95% certainty in our example. In other words, it's the level at which we would reject the null hypothesis that the population mean return is not 9%. So the reason why we use 0.025 and not 0.05 to determine the critical value is because this is a two-tailed hypothesis test. So this sounds a little confusing. Let me show you a graph that will help to better explain this. But before we do that, if you're getting value of this video, please give it a like. It definitely helps out this channel. And if you want to see more videos like this one, let us know in the comment section below. Also, don't forget to subscribe so you can stay up to date on our latest videos. Alright, so I want to explain this graph without getting too technical. If you remember from our third slide, we discussed the lower and upper limits to our confidence interval. You can kind of think of this graph in the same sense, only instead of using a confidence interval range, we're using the lower and upper critical value limits. In other words, if our t-test from before falls within this range, negative 2.045 and positive 2.045, then we can accept the null hypothesis and state with 95% certainty that the corresponding confidence interval around the sample mean does contain a population mean. Now you're probably asking yourself, why are we using both a positive and a negative critical value of 2.045? We were only given a positive one. Well, this type of test is what we call a two-tailed hypothesis test. If we know that the sample mean return is 11%, the hypothesized population mean return can fall on any side of the 11%, which is why we call it a two-tailed test. If we just wanted to know if the population mean was greater than the sample mean, then we would use a one-tailed test. And this brings us to our p-value of 0.025. Because we're dealing with a two-tailed test, we use 0.025 on both sides because when the sum adds up to 5%, which is 1 minus the 95%. So earlier we calculated the t-test to be 0.44. So since that t-test falls within the acceptable range, the 95% range, we can accept the null hypothesis and state that we are 95% certain that the confidence interval around the sample mean contains the expected population mean of 9%, which is what we hypothesized. Now let me show you how to calculate the confidence interval. We should reach the same exact conclusion with the confidence interval as we did with the t-test. So let's go ahead and calculate that. So we're simply taking the values from the example to calculate the confidence interval. There's two parts to this calculation. The only difference is that you change the sign of the critical value of 2.045, which is also called the reliability factor. So after doing these two calculations, we get 1.7% for our lower limit and 20.3% for our upper limit. Our hypothesized population mean return of 9% does fall within this confidence interval range, and this is consistent with the conclusion of our t-test. Alright, so we covered a lot here in this video. This was not meant to be an all-inclusive video on hypothesis testing. Again, the goal here was to go over an example that I think would be a good foundation in helping you better understand hypothesis testing. If you've had any questions about this, please leave them in the comment section below. Also, if you have any other level 1 concepts that you would like to see in a video, drop that in the comments as well. Thanks for watching.